This lecture we're going to be talking about 1D transient conduction. 1D transient conduction for us means that there's a heat transfer in one dimension and there's a change in the temperature profile with time. So we're looking at essentially a 2D problem, but one of the dimensions happens to be time. Remember last time what we talked about was this idea of 0D transient analysis. 0D transient analysis means we are looking at how the body temperature, the temperature of a body changes with time, but the temperature inside that body is uniform, effectively. We took the example of this hot sphere that's quenched in a liquid bath. And in this situation, we start off at some initial temperature, uniform temperature inside that ball. We drop it into the bath. And of course, as heat's leaving, there's a temperature gradient. But importantly, if the resistance to conduction internally is much lower than the resistance to the surroundings, then the temperature distribution inside that ball is basically constant, or it can be treated that way. And so instead of having to develop a model of a temperature profile inside the ball, and then also a model of the temperature to the surroundings, we just assume that the profile inside the ball is constant. And that gives us this 0D transient analysis, right? It's constant in space, but not in time. We justify this assumption just as the same way we did before, using a BO number calculation, where BO is the ratio of the internal conduction resistance to resistance to the surroundings. And I'll just remind you that in order to compute the resistance internally, you can use the conduction length, L conduction. Let's do it this way. You can use the conduction length, L conduction, is equal to the volume of the object over the surface area of the object. And that's a good approximation for the conduction length, if it's not otherwise obvious. Going through this analysis, we end up with a lump capacitance time constant. This is a descriptor of the amount of time that it takes for the object to react to a change in its surroundings. If we want to capture the entire time that it takes to come to equilibrium, we use this 5 times tau LC. Lastly, we developed an analytical model for temperature as a function of time for a specific example. So here we have a body that's starting at T initial. It's exposed to T surroundings, and it approaches T surroundings according to this equation. So today we're going to be talking, like I said, about 1D transient conduction. So let's start by getting some concepts here. Again, let's remember when we're talking about a 0D model, we're saying that temperature only depends on time. So effectively, if I have this body and it's initially at some temperature, let's say down here, it's initially at T initial, and it's then after T initial exposed to some heat transfer coefficient and T infinity, and that T infinity is, let's say, higher, then we're going to start off our initial temperature condition here, this constant value, and then as time goes on, you're going to have this, because it's we're making the lump capacitance assumption, the constant temperature inside the body. It's a constant temperature profile, but that temperature profile just sort of increases like this in time, remaining constant. Right? So this would be like increase here in time. And then this is T as a function of X. So in this case, obviously, T is not a function of X, it's just a function of time. So that's different from the 1D transient case in one important way, and that is in 1D transient, we can no longer make the assumption that temperature is constant or uniform inside the domain. Instead, we have this changing profile with time. So what does that look like? Well, let's plot out on this axis over here. We're going to look at the x-coordinate inside some domain. This is going from 0, and let's say x here just happens to go to infinity. We're not really worried about what's happening on the boundary. So we're going to treat this as basically what we'll call a semi-infinite plane wall. This semi-infinite plane wall starts off at T initial. So let's say down here, we're at T initial, that's right at the bottom axis. And then it's after T initial, it's exposed to T surroundings. So T surroundings for, let's see, T surroundings for time is greater than or equal to 0. So at the very first moment, right, as soon as you expose the surface to the new temperature, what happens? Well, we're fixing the new temperature to be Ts. That's slightly like physically non-realistic that would happen, but let's just, for the sake of argument, imagine that we can do that. So at time equals 0, we've now fixed the temperature at the surface of this body to Ts. What is the temperature profile going to look like inside this domain? So we have had 0 time for any heat to actually conduct into the domain. So if I trace out, let me pick a different color. If I trace out the temperature profile, it's going to look basically like this vertical line going straight down. Right? This here is at time equals 0. So we do have a temperature, but it's basically an infinite gradient. So like I said, slightly physically non-realistic, but for the sake of argument, let's say this is what happens. Now as you go just beyond that amount of time, where time equals 0, you're going to start having the temperature, the temperature profile is going to develop inside the domain. So you have time for heat to transfer in. So after some small amount of time, maybe the temperature profile looks like this. And then after more time, it sort of looks like this. And even more time, it looks like this. So you're getting this temperature profile that's sort of moving as a wave in time into the wall. So we have a few ways that we describe this phenomenon. So first, we're going to say that there's a depth to the distance that the heat has had a chance to conduct, right? So you have this depth to the thermal wave that's occurring. We would call this, for time 1, let's call this delta sub T. This is our thermal depth, and let's say this is at time 1. Right? So this here is time 1, this is time 2, this is time 3. This thermal wave depth, delta T1, describes all the portion of the domain that's been affected by this disturbance in temperature. Likewise, we could just map out delta T2, and that's a different depth. So basically, we have this thermal wave that's propagating through the domain, and our job is to maybe figure out what this thermal depth is as a function of time, and figure out whether or not we can model this entire system as a semi-infinite plane wall. That is, can we model the system as having the thermal wave where it hasn't yet reached some actual wall position over on the right-hand side?